So yeah, what I'll talk about today is, I think, related to several of the talks that we've seen, but maybe more on like a toy setting. And it's basically some thoughts on how we could maybe start analyzing how learning, like machine learning algorithms that learn algorithms would generalize under distribution shifts, and some thoughts on loss functions. So, all right. So, I mean, we are all talking about learning and algorithms here, and this can happen in like a number of different scenarios. So we may be just predicting configurations of solvers, we may be predicting problem parameters, or like using a machine learning routine like somewhere within an optimization solver, or we may actually, like that's kind of the last one here, learn a full algorithm. So basically replace the optimization algorithm with a neural network, for instance. So my talk will mostly focus on the last one, learning a full algorithm, but I think it's like very related to the third one as well. And so what I want to present to you today is not really sort of what I'd call the latest and greatest in terms of experiments. So I've seen very impressive talks in this workshop in what like you can achieve empirically. Instead, what I want to do is I want to start a discussion and thinking a little bit more about understanding the behavior of the machine learning methods that we are using, which will hopefully generalize to the more complicated settings that we've seen as well. So my settings will be much simpler, but I think there's a lot to be said still. And I think like what I'll be talking about is relevant more generally, and I'll be super interested in discussing this more with you. So I call this like indirectly some thoughts on learning for algorithms. So I skipped the motivation on why do we want to do learning for algorithms for this audience, because you all are already convinced. So what I'll do instead is I'll like specify my setup a little bit more. So here, what I'll be talking about mostly is learning with graphs. And so, for instance, my learning, so my data point in my learning problem may be a graph, and what I want to predict is, for instance, the shortest path in this graph. So that each data point in my machine learning problem would be a graph with maybe source and sink marked, for instance, in that case. But in fact, this goes beyond just graphs. In other works, people have also represented general optimization problems via graphs. So, for instance, you could have make a bipartite graph and have the constraints be on one side and the variables on the other side, and then you can connect them with an edge whenever a variable appears in a constraint. So in some sense, like even more general optimization problems, you can represent them in a graph form. So hence, what we'll assume right now is that our input instances are graphs, and then we want to predict something about these graphs. So in addition, our graph here is attributes. So this can be edge weights or some information on the edges, some vector information, and potentially some vector information on the nodes. So what would actually be the learning problem in this case? And because I want to think a little bit more theoretically about some of the things, let's make it simple and simplify this. So for the moment, in the first part of my talk, I'll think about this as a graph regression problem. So while in general, let's say as a running example, I'll take the shortest path. We'd of course want to like predict the optimal solution. Here, what I'll be predicting is just the value of the optimal solution. And I think the analysis generalizes, but this is sort of to keep it a bit more tractable here. So what's our actual learning problem? There's input is that graph with like all the important things marked and all the edge weight information, etc. I'm not learning it right here, right now. And the desired output, what I want my machine learning model to predict is, for instance, the value of the shortest path. So basically the value of the optimal solution of that particular optimization problem that I care about here. So then, like general machine learning setup, I'm getting training data, I'm getting pairs of graphs and the values. And what I want to estimate is that function g of x that gives me the optimal value. And the way I do this is by minimizing a loss function. And there's, of course, a lot of freedom that you have in choosing these loss functions, and some work better than others. For the moment here, I'll just look at this as a regression problem. But what we care about essentially is that if we see graphs that come from the same distribution as my training graphs, I want the loss function on average to be small. And of course, there's some things to be said. What would even be this P if we have optimization instances? And I'll get back to that. And so this is my simplified setting. And of course, there's other things you can tweak around. This is like a simplified learning setting. You can think about reinforcement learning, for instance. You can change the loss function, and I'll do that later. And you can add constraints, etc., etc. So for the moment, we'll think about this as a graph regression problem. So that means that, like in pictures, we have this training data points. Each one is a graph. And we're essentially learning a function over graphs that performs well on predicting the values of these optimization problems. All right. So this is the setup. Here's the outline of the rest of my talk. So obviously, these graphs lead to graph representation learning. So I'll first give you a brief reminder of what are graph neural networks. Most of you probably know it, but just to have everyone on the same page. And then I'll talk about two problems. The first one is a problem that I've seen occur in some of the other talks as well. And this is the question about, to what extent does my model actually generalize to other instances? So let's say in the graph case, I've trained it on graphs of a certain structure. What if I change the structure of the graphs? What if I make the graphs bigger or smaller? And like it sees somehow graphs that look a bit different from what it has seen in the training set. So this is essentially a setting of data perturbation. And now this can happen at a small scale, that the distribution is just a little bit different. Or it can happen at a really large shift, like suddenly my graphs are much larger, for instance. And so I'll talk about this in two different ways. If it's a small shift, it's more a question of the stability of the model. Like there's a small data perturbation, how stable is the model? How much do the predictions change? So that looks a little bit, so I'll be looking at how do we measure even the shift in the data appropriately. And then we'll go into the larger shifts where we have to understand now, like we just know that the data looks very different. So we have to understand something about what the model has learned. And after that, in the remainder of the time, I'll talk a little bit about some thoughts on designing loss functions for discrete problems. So let's start with graph neural networks. What we'll be using here is message passing graph neural networks. They work in two stages. They first encode the neighborhood of each node via a node embedding, and then we get basically a representation of each node's neighborhood, and then we aggregate those representations into a graph embedding. So this is typically called the readout. So the important thing is here, how does this node embedding actually happen? So this, in the message passing graph neural network, this happens via a learned message passing algorithm. So the rough structure is as follows. Let's say I want to learn the embedding of this red node V. So I start with the input features that I have for that node. If I don't have any, I can take a random vector. And then in each round, I aggregate over the information of the neighbors. So all the neighbors send their embeddings to that red node, and it updates the information based on the embeddings of the neighbor. So that's the aggregation and the combine or update operation. And what we're essentially learning here are these two operations. They are parameterized functions. And now all the nodes do this in parallel. So we are really running this message passing algorithm, which has a lot of computational power depending on what the aggregation and combine functions are. So that's the model we'll be working with. And now one form of this that's actually pretty much the most general form is that the aggregation and update function, or this is actually just the aggregation here, is just a neural network applying to V, each of its neighbors separately, and any of the edge information that we have. That's the WVU. So that's MLP, and there is like a small neural network that we are learning. It could be just one or two layers. That typically it's not that large. So that's the learnable parameter. And then the update could be just something like a weighted combination in a fancified form. So that's my model. That's the graph neural network. It's really a learned message passing algorithm. And the way I will mostly view this is by unrolling this message passing operation. So it looks like a computation tree. So going back to the representation of this red node, the red node gets information from the blue nodes and like processes it via this aggregation function. And then the blue nodes have information from their neighbor aggregated via their another aggregation function. And we are applying the same aggregation function to each node within a layer. So this is shared. So now I call this the computation tree, this unrolled, like going back in the iteration, this unrolled operation looks like a tree. So this tree view will be very important. Essentially, what the way the graph neural network sees my graph is via a collection of these kinds of trees. That's how the node representations are computed. So essentially, you could represent all the information that this graph neural network has as a collection of these trees, one tree rooted at each node. So that's one view of this tree. The other view is that actually what I get here is that the actual parts I'm learning are just these aggregation functions. So these are kind of like some small learnable modules or functions, but the actual connectivity, so what feeds into what, is actually fixed. It's given by the graph. So I could also think of this as essentially a fixed template. That's my message passing operation. I know I'm running message passing. I'm not changing that. And the only thing I'm changing is the operation, the aggregation operation that I do in each round. So I call this the structured arrangement of some learnable modules. Okay, so let's keep this in mind. These computation trees are very related to what the graph neural network actually sees about the data. Okay, so let's take now this view of our model and let's think a little bit about generalization under distribution shifts. And I said it's even like not so easy to even define what would be like the right parameterization of a distribution over optimization instances. That's another important issue. So here I'll just assume that like I'm looking at the structure and the features of the input graphs and they look different. So a shift means that they look different from what I've seen in the training data. And we could formalize that a bit more. So what this essentially means is like I have my data distribution and now I'm looking at test data that comes from a distribution with a different support. So this is not only shifting the weights, but it's really a different support. So for instance, I'm training on small graphs because it's cheaper to get the solutions on these small graphs. But now I'm testing. I actually want to run my algorithm, my learned algorithm, on larger graphs or denser graphs, graphs where the actual optimization is maybe more expensive. And this is actually something that also applies to like where we want to learn simulations. It's the same problem. I want to make like running the simulation with a lot of items or particles or like boxes here. It's more costly than with fewer. So I'd ideally train my model with the small ones and then like generalize it to the larger ones. However, it doesn't always work so easily. So that's kind of the problem here. So the size generalization is one instance of this generalization. So, okay, so as I said, in general, this is actually a bit hairy, and this is like a problem, in fact, not only for graph neural networks, it's also a problem for other neural networks, like transformers also have some trouble with this. So, well, under what circumstances may this actually work? If we look, for instance, if we look at changing, for instance, the structure of the graphs. So there's basically two ways in which this can work. The first one, and there's a few works on this, is that the data distribution in training and the distribution shift don't actually look that different. So I said we have a shift, so they are different, but to the neural network, they don't look different. And why is that? Well, because my graph neural network looks at the graphs in a specific way. As I said, it essentially sees the graph as a collection of trees. Now, if the distribution of these trees in their structure looks the same for the small graph and the large graph, well, then the model sees essentially the same kind of data. So to the model, this looks the same. So I'm okay. And you can make a similar argument with the spectral properties that basically, which also essentially is strongly related to the shared structure of the shared local structures of the network. So in those cases, you can prove that you actually get generalization. But what if not? So if not, then suddenly the neural network sees data that looks different from the data that it has seen before. The trees look different. Maybe they have much larger degrees. For instance, that could be one way in which they're very different, or the features are different. So in that case, we have to understand what the model actually learned, and sort of how it would extrapolate essentially that learn function to those other graphs. And then we can try to understand if we can maybe like guide that in a specific way, because it's essentially like looking at a regression problem and predicting somewhere else. So those are the two ways in which it may work. And of course, there's ways in which this can fail completely. And so there's some recent work by Yehuda et al. That shows a worst case scenario. And that says basically if I have two distributions of graphs, and in the new distribution Q, each graph has a tree that's not in the graphs of the original distribution P, the training distribution, then my graph neural network could do arbitrarily bad. So this is kind of very bleak in the sense that, okay, like the structure could change a bit and the graph neural network would like totally fail. So that's kind of the worst case scenario. That means you're essentially, so the way the proof works is that you're essentially showing that you're making a prediction for each tree. And now you have a new tree and you haven't seen that before. So in principle, like if your network is rich enough, you could predict something arbitrary on that tree. So, however, in practice, what we probably assume is that if the trees only differ a little bit, so maybe my Q has a bit of a different trees, but the overall distribution of the trees in Q and in P is not that different, maybe there is a more graded change of performance. And it's not that like I change a tiny bit in my graphs and suddenly the thing will blow up. So the question here that I want to ask is there a way to get like a more smoother degrading, like measurement of the degrading performance than just to say like, okay, this is good and this is bad, essentially. So the black and white. So can we somehow make a prediction about how much the prediction of the graph neural network would change? And that's essentially the Lipschitz constant. So now we are trying to look at some stability of these graph neural networks. And so basically a small perturbation of my data, how much of a perturbation of the predictions of my model would this actually lead to? Now, in general, this is, I mean, I can look at the model and I can kind of figure it out. Now, the trouble here is that we are actually working in a space of graphs. So what is an appropriate metric in the space of graphs to measure this data shift? And there's like many different graph distances I could use. So that's what I want to think about a little bit here. So what we want is we want a good metric or pseudo metric in the space of graphs that is well reflects how the graph neural network would behave in terms of perturbations of the data. So what would we want from this? Essentially, one thing is, of course, it should somehow correspond to like two graphs that are similar in the metric shouldn't lead to extreme like changes in the outputs of the GraphNet. And what we also maybe want is that it includes the blind spots of the graph network. We'll like call this the invariances here. So it's known that the graph neural networks cannot distinguish all possible graphs. Otherwise, it would be too good to be true. So there are certain graphs they cannot distinguish, and maybe my metric also wants them to be the same because it just wants to represent sort of how well do graph neural networks distinguish the graphs and how does their behavior change. If they cannot distinguish the graphs, they will give the same output. So how could we do this? And to do this and have a metric that really kind of is closely related to what the GraphNet does is, I'm going to look at how does the graph neural network view a graph. So as I said, it views a graph as a collection of trees. And well, now we have basically two sets of trees, and we want to measure a distance between two sets of trees. So we'll think about like how to measure distances between sets. And one way to measure distances between sets is via optimal transport. So let's try to do an optimal transport between these two sets of trees. Okay, so here's a reminder of what the optimal transport distance would do. So we have some point clouds xi and yi and yj, and now we want to essentially match them up. So this is more like a relaxed matching problem. So the gamma ij tells me how much I'm matching I and j, and then I have a distance between xi and xj. That's the penalty. And the idea is that I'm moving the pile x, the distribution x, into the distribution y, and I want to do it with a minimal effort. So I don't want to move the points xi too much to match them or move them to the y's, and I don't want to move too much mass. And that's what this matching problem says. And the cost function here is the distance between those data points. So it takes into account the underlying geometry. So it works with sets x and y. And the problem is that now I need a distance between my items of the sets. And my items in the sets are trees. So what I need is a good distance measure between trees. And once I have that, I can just use that formulation. So what distance between trees could we use? And again, there's many choices you could make. The choice we made here is to compute a distance that's very related to the computational structure of my graph neural network. So it's essentially a recursive optimal transport distance, and it works as follows. I have my two trees. I compare their roots with some Euclidean distance, for instance, by just the features of the roots. And then I compute recursively the distance between their subtrees. So now I chop off the root. I have two sets of subtrees, and now I'm comparing those recursively. That's essentially what we are doing. Okay. I call this the tree movers distance here. So again, it's just a recursive distance of these subtrees. And it looks a bit complicated. You have to wrap your head around it, but it can actually be used via dynamic programming. It's not so bad. And you already see that it actually really seems very related to kind of the message passing structure of the GraphNet, because it goes essentially by comparing like the different lengths. All right. So what does this give me? So I have defined now a distance between trees, and I can use it to find a distance to define a distance between sets of trees. So what are the implications? So the first one is this is the pseudo metric, because I'm only viewing the graph as a collection of trees, and there can be two graphs that are not the same graph, but they have the same collection of trees. So those are the indistinguishable ones. But now those are also indistinguishable by graph neural networks, as by the Weisfeld-Lehmann algorithm that kind of measures the distinguishability of graphs of graph nets. So it really sort of reflects the blind spots of graph neural networks, but it also, like for graphs that are distinguishable, it does that like the distance in a graded way. So now I have a distance, which is a distance on all graphs that the graph neural network can distinguish. So let me first show you some theoretical results and then some empirical results. So what I can do now is I can bound the stability of graph neural networks formally by computing a Lipschitz constant. That means if I would change my input graph a little bit, how much would the output change of my graph neural network? So that's the Lipschitz constant. And what you get is you get the distance of the graphs And what you also get is a product of the Lipschitz constants of the nonlinear functions in your graph neural network over the layer. So that's the K. And this looks very similar to what you'd get for fully connected networks, where there, like the TMD, the tree movers distance would be replaced with the Euclidean distance. The second thing you can do is you can look at learning theoretical bounds we have from domain adaptation. So this is a cross-domain generalization bound. So the idea is that I have some source distribution, and I'm measuring the risk on the source, meaning the loss function on the source distribution, but I'm actually interested in some other distribution, the target distribution. Typically, I don't have labels on the target. And so now I want to relate the risk or the loss on the source to the loss on the target. And the way you can do this is by essentially looking at a divergence between the source and target distributions and the Lipschitz constant of your model. So that's the lip of H. H is the learn function. And now this domain discrepancy, how different is the source from the target distribution, can be again measured by the tree movers distance, because these are two distributions of graphs. And again, once I have a distribution over graphs, I can use the graph distance to define a Wasserstein distance. And now the graph distance itself is defined via optimal transfer. So we obtain these theoretical bounds that show us, that help us to like bound the stability of the graph neural network, to bound like the loss on the different, on a target distribution that has a distribution shift. So these are theoretical bounds, and admittedly, like those, like product of Lipschitz constants or so, these bounds are, can be somewhat loose in some cases. So let's look at some actual like empirical examples and see, like, does it actually say anything empirically? So I have to admit, these results are not on optimization problems. We haven't tried that yet. These are on regression for molecules. So we have like input graphs and we are predicting something else, properties of these molecules, but it's graph input data. So, and I'd be happy to like discuss this further in the context of optimization, because I think it's still relevant. So let's look at some of these empirical results. So what we're comparing here with here is a different metric. It's called the Wasserstein-Weisfeiler-Lehmann metric. So what that does is essentially compute embeddings via graph neural networks and then compare the embeddings in a Euclidean way. And so the top row is the tree movers distance, the new one, and the bottom row is this Wasserstein-Weisfeiler-Lehmann metric. And now what we're measuring is how much does the distance in graph space correlate with the change in the output. And you see that the top row, it's basically a much better correlation than at the bottom row. So the tree movers distance is more aligned with the changes in the output of the graph neural network than the other distance. And we can likewise do this by looking at the second one, basically, if I have a domain shift, how much would my accuracy drop? So this was kind of related to the second bound I have. And in this case, this is just a correlation. How much does the distance correlate with the accuracy drop? So how predictive is it for the accuracy drop? We get a better correlation for the tree movers distance than for the other distance, which is kind of the closest competitor, essentially. So what these results essentially show is that if I want to measure how much like my performance would degrade or how much my outputs would degrade, like what's the stability of my model, it helps to actually think about how does my model actually see the data? What part of the data does it actually see? And can I measure like a meaningful change in that part of the data that's actually relevant to the model? And I'm kind of ignoring everything that the model is also ignoring. And that way I can get a bit sharper results than otherwise. So in some sense, I already here tried to understand what the model is doing and try to bring this into my distance function to measure perturbations. But this really, like the stability bounds in like measuring how much does my data change and like correlate this with how much does my model output change, this is most relevant in the regime where you have small perturbations of the data. So what if we have large perturbations? So let me show you some ideas about that. So this is some older work of ours, but I think it's still relevant for this audience. So if you haven't seen it, I think it's useful. So what's the problem if my data is very different? So I like to compare this to this regression problem. Let's say we had like a one-dimensional regression. We have a lot of training data in the blue box, and we can fit basically any function in this blue box. And now I'm asking the model, what would you predict where that red star is? So that obviously depends on what kind of function I did my regression with. Was this a polynomial? Was this a cosine or periodic function? What order of polynomial was it? Was it maybe a piecewise linear function? So depending on what I used for my regression, that will determine like what my prediction of that red star will be. So essentially, I have to understand the inductive biases of my model because I'm not giving it any information to fit. So that's basically the second part of that big picture when the extrapolation may work. And I mean, this is obviously, admittedly, a very complicated problem. Understanding inductive biases of neural networks is a big and like challenging problem. We have to understand the learning algorithm. We have to understand kind of the architecture and the data and all of that interplay. So to make this a bit tractable, I want to use the idea of the algorithmic alignment. And this is basically looking at the computational structure of my graph neural network again and relating it to the algorithm I'm actually learning. So going back to my running example of shortest path, if you look at the Bellman-Ford algorithm, for instance, in its computational structure, it looks extremely similar to my graph neural network. In each iteration, I'm doing something on each node. I'm updating some information about each node, which in this case is the shortest path that I've found so far. So because the computational structure matches so closely, it's actually, that's one of the reasons why you can learn such an algorithm very well with the GNN. Essentially, the GNN can mimic that algorithm just by learning that last line. And that last line is not such a complicated function. It's a min over the neighbors. So this is the idea of algorithmic alignment. Essentially, the computational structure of the neural network and the algorithm that I want to essentially mimic matches in some way. And we've seen it in other talks too, where the speaker said that, yeah, it actually, if you think about the architecture, you can do better, essentially. So a targeted architecture can usually do better. So I want to just use that viewpoint to make my analysis a little bit more tractable. So I will now just look at these learnable parts, what they do, and then, so basically the last line, that's the aggregation function in the network, and then bring this back into the big picture. So just that. And that's just essentially an MLP, a fully connected network, applied to the node features. So what does a fully connected network do when the input data is out of distribution? So I have a distribution shift in my input data. And now I'm just doing this for one single MLP, which is part of my aggregation function before the summing, and then I will put it back later into the full model. So here's a simple experiment with learning some super simple function, quadratics, cosines, etc. And what I'm looking at is if I train my neural network in some range of the data, and then I just shift my data, so I shift it in Euclidean space, and I look at the extrapolation, what does my model do? And you see that here, for all the nonlinear functions, we are not doing very well, and for the linear or piecewise linear functions, sometimes. This has to do with the fact that this is a ReLU neural network. So what is actually going on here? So here's the picture of what is going on. So going back to my regression model, where I have the training data, the model fit, like these are simple functions, it's going to fit it very well. But as I go away from my training data, the model, because I have a ReLU network, extrapolates like a piecewise linear function. So essentially directionally linear. It means it concentrates all the nonlinearities where the training data is, because that's where I have to fit the data. And here's the picture in higher dimensions. So here, this is like an empirical thing. So you can check that empirically, but you can also prove this in a simplified setting. This is with a neural tangent kernel. That basically, as you go away from your data, the function becomes just directionally linear. So what does this mean for like the inductive biases and the extrapolation? So first, what it means is as you go away from your data, these nonlinear functions that I'm learning look more like linear functions. And second, there's also some implications on the training data geometry, meaning what kinds of graph structures I'm actually training on that has an impact on what kinds of functions I can learn. So basically, because I have a lot more degrees of freedom, this is a ReLU neural network, I need enough support in all directions. So let's now take this, especially message number 1, back into our graph neural network. So again, let's assume we want to learn the shortest path algorithm. And so we want to directly align. And maybe Petar later in his talk has some more examples of this. So he has worked a lot in this direction too. So we want to mimic the shortest path algorithm. That means we essentially have to learn a function that is the min over the neighbor's features with some addition of the weight, edge weight. So a GNN can model this. So my MLP can model this, but the MLP has to be a nonlinear function to be modeling this. So which means, as per what I said right now in the previous few slides, it will work very well in my training data, but it will not work so well on out of distribution data potentially. That means if the inputs to the MLP are out of distribution, which may happen, for instance, if your degrees are different or the node features are different. And indeed, this is what you see empirically. So here, these two plots show on the left-hand side the error. If the training and test distribution are the same, you get very small error. If the training and test distribution are different, then suddenly you get a much larger error. So it generalizes very well in distribution, but not out of distribution. However, if you actually look at models that were empirically that they have successfully extrapolated, these models don't use a sum in the aggregation function. They use a max. And if you use a max, you can model this min with the MLP being a linear function. And now in the green case, we see that both in training and in test, we actually get low error. So that green one extrapolates much better. Well, what did we do here? We tried to kind of understand what the model is doing so that when like the data shifts, it may look more like a linear function. And now if I actually adjust the architecture of my model in a way that MLP being a linear function is okay, then I extrapolate better. So I've tried to understand a bit of what the model does and adjust the architecture accordingly. Admittedly, that needs more information, more thought about what you actually want to model. And this is actually a pattern that you can see not only in the example case I showed you, but across many different examples of learning with neural networks. When you get successful extrapolation, often the architecture is much more targeted and what you're learning looks more like a linear function. And there's also some interesting connections with representation learning, where maybe you're learning actually a better representation that makes the subsequent task more linear and brings sort of the out of distribution data closer to the in distribution data. And the same would happen with like modeling invariances, etc. So that was my second example about the out of distribution generalization. So both of these examples, the stability and the understanding the parts of the neural network, really try to understand what your architecture is doing. How is it seeing the data? What kinds of inductive biases does it have? And can we somehow translate this into better understanding what the architecture would do when I have shifts in the data distribution. And that hopefully can give me also some clues about what kinds of instances can I generalize to and what maybe not. And this is, of course, these are like some ideas, some partial answers, and I think there's a lot more we can say about that. But I don't want to philosophize more about this right now. I want to just briefly shift gears and talk about another topic, and that is thinking about the loss functions of neural network for learning discrete optimization problems. So to think about this setup, think about, again, a graph optimization problem, but now what we actually want to predict is not just the value, but we actually want to predict the solution. So often the solution is maybe a subset of the nodes or a subset of the edges of the graph. So, well, if we look at this as an optimization problem, what this typically means is we have some function that gives us a penalty on a subset of nodes or a subset of edges. So we have a set function that assigns values to sets. Now, if we use that, of course, like we could just train a neural network with that as the objective function, as the loss function. That's what it's supposed to optimize, so just use that as the loss function. Now, the problem is that this is, of course, a function on discrete inputs, and this doesn't work very well with neural network training. That's, of course, not a new insight. It likewise doesn't work well with any kind of continuous optimization method. So, like the standard way, what to do in this case, or one of the standard ways, is well to relax the problem. So we have a function that's defined on the hypercube, and we find a so-called extension. Think of an interpolation that works on the continuous space of like between 0 and 1. So here's an example of what this could look like. This is a cut function on 2 nodes in a graph. And here is a nice interpolation of this. This interpolation is continuous. It's actually very nice. It's smooth. I could just use that as a relaxation. And there's actually different ways to do it. Here's another one that's convex, is not smooth. Both of these are valid extensions. So there's actually a range of extensions you could come up with. So that's, so this is for nonlinear set functions, like the cut function as a function of the nodes. If you have a linear function, this would just correspond to an LP relaxation. So what do we want from this relaxation? We want that it is continuous, because otherwise it's, again, a bit difficult to use as a loss function. And we want that it's an actual interpolation, meaning in the discrete points, it should coincide with our set function. That's what these won't satisfy. Now, again, this is just background. There's actually a general strategy how I can design such an extension in the nonlinear case. If f of s is nonlinear, I basically define the little f, the extension, as an expectation over evaluations of my set functions. So I'm defining a distribution over sets, which is parameterized by my x. X is the thing that lives in like the continuous vector in 0, 1. With n coordinates, where n is the number of nodes I have in my graph, for instance. So I define this as an expectation. And what I often also ask is that the x is actually the marginals of that distribution. So xi, the I coordinate, is the probability of item I being included in the set. But of course, even if I have the marginals, there's a lot of different ways of having different distributions with the same marginals. So the question is, how do I couple these instances, the items? And so on the left, actually, the plot that I have is that when you have an independent distribution, so all the items are independent, it's a product distribution. On the right, what this actually is, this is the so-called Lovász extension of that cut function. And that's not where I see all the items being independent. This is actually where I'm coupling them in a specific way. And your LP relaxation would actually correspond to the product distribution. So Okay, so this is the way I could design a relaxation, and now I could maybe have my neural network work in the X space and just basically like predict the X and then like round it later. So, okay, let me just give another overview in a different way. What we've done, we went from a function over sets to a function over the hypercube, which is continuous and an interpolation. And we could train our neural network with that as the objective function. So this can actually be done. And there's only one thing about this. And this is that if you look at neural networks, they really like high dimensional spaces. And here the vector X is still, if I have n nodes in my graph, for instance, it's going to be n dimensional. It's going to be not that large. So we also tried another thing, and this is using instead a PSD matrix. So this would be at least an n by n matrix. And now you can extend that definition of my relaxation, my extension, to matrices. So that's what it would look like. And now what we are essentially asking is that if I take the outer product of the indicator vectors, that corresponds to the function value. So it's again an kind of interpolation. And that's what we'll actually, what we found works much better. How did I get there? So the way you can derive this extension I told you about is basically by looking at the convex envelope of that set function and then taking the dual of that problem. So this is what it looks like. And y is essentially that distribution. So the ys gives you a value for each set. And that value will be between 0 and 1. And that's essentially, you can view this as your P of S. And now you can parameterize it with that X. So now how do we go from there to a valid matrix extension? So we could use the SDP version of this. So this essentially gives you some kind of SDP version of the Lovász extension of the submodular set function. And now if I had a valid vector extension, so something that's basically like the ones I showed you where you have the relaxation over vectors, then I can actually get a relaxation over matrices. And the way I can do this is by looking at a decomposition of the matrix, for instance, the eigen decomposition. And then I'm just taking a linear combination of the extensions for each eigenvector. So each eigenvector is a vector. I can use this vector and say, well, this is like a vector relaxation. And now I use the distribution defined by that eigenvector. And that gives me the matrix extension. So now the eigenvectors don't always have entries between 0 and 1. In some cases, it doesn't matter. If it matters, what you can do is you can send it first through a sigma. So I don't have a lot more time, so let me just show you some empirical results and then conclude. So how does this actually work? So here's a comparison between the green one is the vector extension and the yellow one is the matrix extension, and training a neural network on a simple Max-Clique problem to compare these. And what you can see is that the matrix extension is very competitive and often better. And our reasoning is that this is in a higher dimensional space. This is also not a new insight in both in machine learning and optimization. If you go into a higher dimensional space, the problems often become easier. And here's another example with a K-clique problem. All right. So let me conclude with that. What I showed you hopefully gave some ideas on trying to better understand what neural networks do when they learn discrete optimization, especially discrete optimization problems, but maybe you can also generalize this to continuous ones. Both by looking at the data geometry, by looking at the model architecture and how it actually corresponds to the algorithm you're learning. And finally, looking at the loss function as well. So I think all of these are ideas. And all of this was in a setting where it's tractable and nice to analyze. And a lot of the other talks have settings that are really practical and much more complicated. And I'd be very interested in like thinking about how to extend these results to some of the more complicated settings. I think it can be done, at least in some cases. I'm happy to take any questions now. I'm also happy to chat more. Just send me an email and we can set up a time to chat more. Thank you.
Thank you, Stefanie.